Alright, this is a final review of how to do a chi-square test for your test that's tomorrow. Your short answer will have a chi-square test and it'll look very much like this. It will probably be a dihybrid cross, meaning one that has two traits rather than one, but there's already a tutorial of a dihybrid, so I'm going to do this one as a sample for tomorrow's test. So they're going to give you information. So they tell you tall is dominant to short. Then they say that a tall plant crossed with a short one yields the following offspring. And you will notice the table is there, and it's already partially filled out with the observed offspring. And that's really important because you oftentimes need to see the offspring to figure out what the parents are. So first, we know that tall is dominant to short, so the tall plant has to have a big T. It's crossed with a short plant, so the second plant has to be little t, little t. To figure out whether the original plant here is big T, or big T, little t, we look at our offspring. Notice how some of the offspring are short. And the only way that you can get short offspring from this cross is that this parent had to be big T, little t. So the first point that you'll get on the test will be for correctly predicting the genotypes of the parents. There will then be a little section off to the side that'll literally say predicted ratios. For predicted ratios, I want the fraction or percent that you would expect in this cross to come out tall versus short. So I'll just do a little Punnett square of this information. We're crossing big T with little t, little t. And you'll notice that we expect half of them, or 50%, I don't really care if you put half or 50%, to be tall versus short. That'll be your second point for your predicted ratios matching your predicted parents. The next step in your chi-square test is to fill out the table. So if we had 600 offspring observed, then our expected needs to also be out of 600 offspring. In other words, we want to know how many of the 600 should have been tall and short based on our predicted ratios. Now in this particular cross, we predicted half and half. So this one's going to be really easy. So half of 600 is 300. And again, the other half of 600 is 300. So our expected in this is going to be 300 of each. Keep in mind it's not always going to be even like that. Had we predicted, let's just say 3/4 to be tall, then you would be multiplying 3/4 times 600 to get your expected. The next thing that you're going to do is you're going to plug those numbers into the chi-square formula, and you will have the formula sheet to do that. Remember that it's observed minus expected squared over expected. So I'm going to skip ahead and just fill out the answers on this. So chi-square would be 2.43 for this one, and it actually comes out to the same number for the second one. It will not always do that, so don't just work out one and then assume that the rest are all going to be the same, because they are not necessarily going to be the same. You're going to add those together to get your final chi-square answer, and that's going to be 4.86. So this will be the next point that you would get on the test for properly calculating chi-squared. Now that you have chi-squared, you need to know your degrees of freedom. So your degrees of freedom is the number of outcomes, or in this case, phenotypes, minus 1. So there were two phenotypes, tall and short. Minus 1 gives us 1 degree of freedom. And then you have to go to the table, which I did not print a copy of here, but if you'll recall, you'll have this in front of you. Across the top are the degrees of freedom. And then over to the side, it's the 0.05 row that you want to look at. So that's going to give us our, what we call our critical value, which is our cutoff number. And so in this case, if you go to the table to the 0.05 row, you will see that the critical value, I believe, is 3.8 something. Let me see. I should have written it down. 3.84. So 1 degree of freedom, 3.84, and so that's our critical value. Since our calculated chi-square is bigger than the critical value, we reject. Keep in mind that purposely some of these are going to fail the chi-square test. It does not mean you did anything wrong. The whole point of a chi-square test is to see if the offspring match up to the genetics pattern that we think it is. So the fact that this fails could mean that it's a sex-linked trait, or there's a second gene involved that we were unaware of. There's lots of reasons that it could fail a chi-square test. It doesn't necessarily mean you did the test wrong. So please keep that in mind on the test tomorrow, that if it fails, it doesn't necessarily mean anything, because some of them are going to purposely fail. Okay, the other thing I wanted to clarify is pedigrees. So you have to, this will not be on the short answer, but on the multiple choice, there are a couple of pedigrees where you have to classify the pattern of inheritance. So just to clarify, the whole point of a pedigree is you're sort of like a detective, and you're trying to figure out how a particular trait is being transmitted through a family. So you have four options. The trait could be autosomal dominant, meaning that everybody that has a copy of Big B has the trait. The trait could be autosomal recessive. So the only people that have the trait are people who are little b, little b. The trait could be sex-linked dominant, in which case females would have to have at least one Big B to have the trait, and males would be X big B Y. Or the trait could be sex-linked recessive, where females would have to be X little b, and males would have to be X little b, Y. That's your whole goal. If they don't tell you what kind of pattern it is, that's what they're asking you to do, is to figure out how is this trait being transmitted. So a lot of it can be trial and error, but there are some clues you can look for. The first one in this specific pedigree is that this trait skips generations. What do I mean by that? What I mean is, if I look at generation 1, nobody shows this trait. And then if I go to generation 2, I see that they had 2 children that have this trait. As soon as you see that happen in a pedigree, it tells you that the trait has to be recessive. Why? Because if the trait was dominant, let's just pretend like we think it's dominant, that would mean that everybody that's colored in is Big B something. It's not possible to have 2 parents that don't have the trait, little b times little b, produce a child that does. So that rules out the possibility that this is a dominant trait. This has to be a recessive trait. If we rework this with the trait being recessive, then again, this is sort of trial and error. Let's see if it works. If the trait is recessive and this child is little b, is that possible from these parents? Yes, it is, because the parents could be carriers of the trait and then make a child with the trait. So anytime you see that a trait skips generations, that tells us automatically that this is a recessive trait. So I can cross out autosomal dominant and sex-linked dominant from my options. And that's my recommendation, is the first thing you want to do is determine if it's dominant or recessive. Then you can go to the second step of sex-linked or autosomal. Now, this happens to be autosomal. There's a lot of clues, and again, I can show you some trial and error, but the biggest thing that's going to tell you that a recessive trait is autosomal and not sex-linked recessive is what happens with males. Do males that have the trait, so you go through your thing and you find a male that has the trait, which is here. This male has the trait. If he passes it to his son, which we see here, and mom does not have it, this cannot be a sex-linked trait. In other words, if we start it, let's say we think it's sex-linked recessive. He could, well, actually it doesn't work anyway, because I just realized that if it's sex-linked recessive and he doesn't have it, he'd be X big B Y. She doesn't have it either, but she could be a carrier of it. Could they make this female? No, because dad is definitely going to give X big B to all his daughters. So it's not possible for this to be sex-linked recessive. But the other way you could figure this out is this male has the trait. So if this was sex-linked recessive, he would be X little b Y. Mom does not have the trait. So we're going to make her X big B, X big B. If this male has a son, he's not going to give the trait to his son. He's going to give the Y chromosome to his son. So the only way that a son could have this trait is he would have had to have gotten it from the mom, and we don't see mom having the trait. Now technically you could argue that she could be a carrier, but what you're going to see if a trait is sex-linked recessive, typically, is you're going to see a table that has mostly males colored in. So you're going to see it's going to skip generations, and you're going to see a male have it, then nobody has it, then a male have it again. And pretty much you're going to see a tree where probably only males are colored in the tree. Because since males only need one X to show the trait, males are going to be more likely to show a sex-linked recessive trait. So now that we've ruled out sex-linked recessive, our only option is that this trait is autosomal recessive. So we can double check to see if that works. So if the trait is autosomal recessive, that would mean that the people who are colored in are little b. Is that possible that these parents could have that child? Yes, because they could both be carrying it. We don't know what this child is. He could be big B, or big B, little b. But this child has it, so they also are little b. And they have a child with it, so we know mom must be a carrier of it. So it works. So again, there are clues you can look for, and I went through these clues the very first day. I will write them down again for you to figure out if a trait is dominant or recessive. Look to see if it skips generations. If yes, the trait is recessive. If no, then the trait is dominant. Now, once you've got dominant or recessive, how do we determine sex-linked or autosomal? If the trait is sex-linked, you're probably going to see males have the trait, females don't. Also, you're going to see no father with the trait passing the trait to their son, because that cannot happen in a sex-linked trait. If it's autosomal, you should see males and females, probably in similar numbers, and males would be able to pass it to anybody, so you would see males passing to sons. This does not mean males can only pass to sons. I'm just saying that if you see a male passing to a son, it rules out sex-linked and tells you the trait is autosomal. It doesn't matter what the females do, because since females have two X's, they're going to pass on a sex-linked trait the same way they would pass on an autosomal trait. But a male is going to pass on a sex-linked trait differently than he's going to pass on an autosomal trait. Because a male with an autosomal trait is going to have two copies, and he's only going to have one if it's sex-linked. Now, if you determine that the trait is dominant, then your rules are a little different. If the trait is sex-linked, a male that has it will give it to all his daughters. Why? Because if the trait is dominant, he's going to be X big B Y, which means he's going to give his sons the Y, but every single daughter is going to get his X. So males will pass sex-linked traits to all the daughters. That's a big clue that you can look for. And again, there will be no males passing to sons. So if you find a father that has the trait, mom doesn't, look to see if he passes it to the son. If he does, it cannot be sex-linked. If it's autosomal, then you'll see similar numbers of males and females that have it, and you will see fathers can pass to sons. So I hope that helps to clarify it if you were still struggling with pedigrees. But again, all I can tell you is worst case scenario, just do it by trial and error. The dominant recessive part is pretty easy. And then the other part, you may just have to try plugging in. Say, okay, I know it's recessive. Let me see if sex-linked works. Start assigning what everybody's genotypes would be. And typically you're going to get to a point where you realize it's not possible, either as a sex-linked or as an autosomal, and you can rule one of them out. So hopefully that's helpful.